Okay, for this lesson we actually have like three different parts. Our first part is talking about cofunction identities, and those kind of go hand in hand with the identities that you kind of know of. So sine and cosine will go together, tangent and cotangent will go together, and cosecant and secant will go together. A little bit different than usually we group sine and cosecant together and cosine and secant together. This time we're going to talk about how these functions behave in our triangle, and you'll see why in a second. Our second part is dealing with the trends, so how our functions behave as we continue, as our angle increases. And today we're only going to focus in quadrant 1, and then tomorrow you'll focus in the other quadrants 2, 3, and 4. But today, again, in quadrant 1. Both these things, and in the back we'll talk about kind of relate to our special right triangles and how we can have those special right triangles in our unit circle and how those appear as far as coordinate and sine and cosine points are concerned. So again, one of the things that you should be thinking as we go through our chapter is what kinds of things could you be asked to explain. Those derivations are definitely free game, something that I could ask you to explain how those things relate and how we came up with these identities. So maybe you focus on, at the very end, when you're studying all your stuff, you focus on how we came up with that derivation and explain or show this process, and then maybe you focus on how we explain the trends in quadrant 1. Both these things, again, are fair game as far as explanation problems. So to start out with our derivation of our cofunction identities, we are going to list some of the ratios that we know in this triangle. So across from angle A, I'm going to label that as side length A, side length B across from B, and side length C. Now if I'm standing at this angle, I can come up with my trig functions. So I know that the sine of angle A is going to be my opposite, which is A, over my hypotenuse, which is C. So I know that that ratio is true. And I can also come up with my cosine of A. So if I'm standing at that angle, my cosine would be adjacent, which is B, over my hypotenuse, which is C. So now I'm going to switch it up, and I'm going to stand at a different angle. I'm going to stand over here at angle B. So if I stand at angle B, I have a different sine and cosine because my opposite and my adjacent are switched. So my sine of angle B is going to be my opposite over my hypotenuse, which is B over C. And if I'm standing here at angle B again, my cosine will be my adjacent, which is A now, over my hypotenuse, which is C. So you should see some similar things that are happening as we came up with our ratios depending on what angle we're standing at. So our cofunction identities deal with the different angles in our triangle. So I know that the sine of A and the cosine of B actually produce the same ratio. Those actually end up being the same value. I could say that the sine of A is 1/2, and that would also mean that the cosine of A would also be 1/2 in this particular triangle. If, say, my A value was 1 and my C value was 2. That's a possibility. So these ratios that appear, just what happens is that we're just standing at a different angle. So if I write that out, like this is one of our one of the things that we're seeing is that the sine of A equals the cosine of B, and vice versa. Cosine of A equals the sine of B. These things are also produce the same ratio. What we want to come up with some generalization is to somehow relate A and B together, angle A and angle B. So as you're looking at that triangle, there is a relationship about the angles or the, what these two things are. We know that they're both acute angles, for sure, because they're in this right triangle. These angles definitely can be obtuse. Knowing that this angle here is 90 degrees, we also know a certain thing about all three of our angles in a triangle. They all should add up to 180 degrees. I already know that this angle here is 90 degrees, so these two angles that I have must also add up to 90. These two angles must be complementary. So that's another thing that we know is that A plus B equals 90. And that will give us a relationship which will actually derive our cofunction identities. So if I say instead I want to replace B and make the substitution, I could solve for B in this case. So subtract A from both sides. Take that stuff, put it in for B. And then this is one of our cofunction identities. Now we have this equation that relates our sine and cosine in any particular angle. So again, if I know my angle, say, is 20, so the sine of 20 would also equal the cosine of 90 minus 20, which is 70. So sine of 20 equals cosine of 70, and that will give us that relationship. This also means that the sine of 45 equals the cosine of 45, which should make sense because the sine and the cosine values, these opposite and adjacent values, would be equal to each other, which means that my sine and cosine would still be some ratio of A over C or B over C, and if A and B are the same, then it's definitely the same ratio. That's kind of the turning point. And then it'll kind of cycle back. So sine of 70 would also equal the cosine of 20. So we can see that kind of relationship where they interweave at one point and then everything kind of flip-flops from there. The same thing happens, like you could come up with the same idea for tangent. And I'm going to write it this way with A in our answer, but this could also be some generic theta. I think that's how your book actually defines it, as sine of theta and cosine of 90 minus theta. But either way, it shouldn't make sense. It's just some angle. And then cosecant equals the same kind of idea, same cofunction identity. This would also mean that the sine of 90 minus A equals cosine of A as well. So they also flip-flop in that same direction, because I could have just solved, instead of solving for B, I could have solved for A and then replaced it there for my angle. I think the easier way to remember these things is that these two angles, sine and cosine, the angles that we're actually, the argument that we're taking, those angles are complementary, so they add up to 90. So for this example, if I'm trying to figure out what this angle would be, I know that the two angles, 40 and x, add up to 90. And I think that's an easier way to describe it than looking at this. It essentially just means the same thing. So if I solve for x, I get 50. So the sine of 40 would be the same thing as the cosine of 50, because those two angles, A and B, are complementary. So same thing here, secant and cosecant, those two go together. I know that these two angles have to add up to 90. And I can solve for my missing x value, which I should get 10. And again, same idea. These two angles are complementary because they're still in kind of my triangle. This one's a little bit harder because we have an equation we have to solve for, but we can add them up, set them equal to 90. We'll get 4x plus 6 equals 90. Subtract 6 on both sides. 86, and divide by 4, and this should be not 86, 84. Divide by 4 and you'll get 21 for your answer. So that's part one of this lesson, is kind of understanding how this derivation works, how we came up with this cofunction identity. And again, basically that all that comes down to is, depending on what angle you're standing at, your ratio will just end up flipping between sine and cosine. And those two angles that you're standing at are complementary. So we can come up with this relationship between the two angles and between the sine and cosine, the two different ratios of the two different triangles, because they produce the same ratio depending on where you're standing for what angle. So keeping that in mind, we're going to look at the trends in quadrant 1. So we've already talked about these particular values that we're looking at. So I know that, like, on our quadrantal angles is what I mean. As I'm standing at this quadrantal angle of 0 degrees and I'm going to look at 90 degrees, I know that this coordinate point is 1, 0. And then we already talked about that this x value here was our cosine value, and this was our sine value. And likewise, at 90 degrees, my coordinate point is 0, 1. And again, this would be my cosine value and then my sine value. So if I'm looking at my sine value in particular, I know that my sine value is at 0 degrees, it's at 0, and then it's going to 1. Our sine value at 90 degrees would be 1. So as I'm increasing, as my theta, my angle, is approaching 90 degrees, as my theta increases, my sine value approaches 1, which also means that it increases. Now I'm going to talk about why that actually makes sense. So if I'm thinking about the unit circle, I also know, this is kind of going to come into play more on the back, but I can draw in triangles that hit this unit circle. So here are my triangles that are being formed. Okay, and they're all right triangles. These would be my reference triangles in my triangle, or in my unit circle, quadrant 1. Now I know my sine value goes along with my y value, and as I'm looking at my y value, my opposite side of these triangles, what's happening? They're getting bigger as I'm approaching this value. So it makes sense that as our angle is increasing, as our angle in reference to our terminal side and our initial side, which is the x-axis, as that angle is increasing, my y value, my opposite side, my sine value, is also increasing. The opposite is actually true for cosine. So as my angle increases, as I'm getting closer and closer to 90, going this way along my unit circle, my cosine value goes from 1 to 0. So you can kind of see that in my triangles. My adjacent side, instead, is actually getting smaller and smaller and smaller. So this instead decreases. Ooh, what about tangent? Because tangent's a ratio. Tangent, again, is something we've looked at this as a quotient of sine and cosine. So thinking about that, deciding whether that is going to increase or decrease, well, I know that I have something as I'm going forward to 90 degrees, I have something that's increasing over something that's decreasing, and this is in quadrant 1, so I'll write that in quadrant 1, because it's not true in every quadrant, but at least in quadrant 1 I have something that's getting bigger over something that's getting smaller, and something that's getting bigger, a bigger value over something that's smaller, is also going to increase. So we're actually going from a tangent value of 0, which is sine over cosine, to something that's 1 over 0, which is undefined. And as I'm dividing by something that's getting infinitely closer to 0, dividing by something small will actually give a large quantity. But this might be something that you might have to explain on a test. So tangent increases because it's the ratio of sine over cosine, and sine is increasing, getting bigger, and cosine is decreasing, so the ratio of increasing over decreasing will increase. Will get bigger as well. So again, that might be something that you might have to explain. Or when we talk about quadrants 2, 3, and 4, maybe that's something also that you have to explain, is why the tangent, decreases in quadrant 4, or why it increases in quadrant 3. Like whatever it is, you might have to explain this in the same way of increasing or decreasing. Or maybe I ask you about cotangent. What happens with cotangent? Or cosecant. What happens with cosecant if I have something that's decreasing? If I have cosecant, I said. If I have something that's sine values increasing, and then I have the reciprocal of that, what actually happens to cosecant then? You might have to explain all of your trig functions in quadrant 1. So that's something that you should be keeping in the back of your mind, and maybe as I'm saying that, you're coming up with an explanation of why those things increase or decrease. The actual math part of explaining or comparing the two identities uses the idea of whether it's increasing or decreasing, but it's more in like a numerical sense. So if I know that our sine value as I go from 0 to 90 increases, that means that my sine of 23 degrees would be like, here, and then I'm looking at something a little bit bigger, so my opposite side is going to get bigger, so that means that my sine of 23 is going to be smaller than my sine of 24. Because my angle is bigger, so my sine value is also bigger because it's producing that bigger opposite side. But again, the opposite's true for my cosine. As I'm getting a bigger angle, my adjacent side is getting smaller, my x value is getting smaller. So in this case, as my angle gets bigger in quadrant 1, then my cosine value is going to get smaller. So a bigger angle would produce a smaller cosine value, which means that my cosine of 23 is going to be bigger than cosine of 24. That should also make sense too, because these should, since we have these cofunction identities, they should reverse directions. Again, we talked about how at 45 degrees these things are equal, so it kind of like gets bigger, or sine gets bigger, and then at 45 they're the same, and then it gets it's getting bigger still, but getting bigger at a smaller rate. Same thing for my cosine; they kind of cross over, so they should have reverse behaviors in quadrant 1 trends. Again, this idea of tangent, so I have an angle, and then I have another angle of x plus 3. So if my x is like 10, then I'm comparing tangent of 10 and tangent of 13. So this x plus 3 is going to be a bigger angle, and we just found that a bigger angle also produces a bigger sine. So our tangent of x plus 3 is going to be bigger than the tangent of x. Ooh, example 7 compares sine and cosine, which we can't quite do that, but we already learned that we have a cofunction identity that compares sine and cosine together. So instead, if I want to either put this in terms of cosine or this in terms of sine, doesn't really matter. I do know that I'll do them both, so we can compare them both. So I can compare both these in different ways. So I can transform cosine into a sine value, and remember that this angle and this angle, whatever it is, have to add up to 90. So I can solve for that by doing 90 minus this, and I should get 15. These should be the same thing. Those are equal because they're cofunction identities. Or likewise, my sine of 20 would equal my cosine of 70. So then I'm comparing these two quantities or these two quantities. So again, if we're thinking about quadrant 1, and as my angle is getting bigger, my opposite side, my triangle is growing in length, or as far as tallness is concerned, my opposite side's getting bigger, my y value is getting bigger. So my sine of 20 would be bigger than my sine of 15. And then again, the opposite's true for cosine. As my angle is getting bigger, so this is my bigger angle, my adjacent side is getting smaller. So this side length, or the cosine of 70, a smaller angle, would produce a bigger value. So we're still opening towards this side, the sine of 20, which again is equivalent to the cosine of 70. So you could do it two different ways for that one, but you should still get the same result, that this quantity is bigger than that quantity. So that is question, or part 2 of today, is looking at the trends. So the first part again is that cofunction identity, which we use down here, and then looking at the trends of whether things are increasing or decreasing only in quadrant 1 right now. And again, that's a good explanation problem that you should be prepared for. So on the back, we're going to look at our unit circle and then combine the stuff that we learned yesterday, the special right triangles, in with our unit circle idea. So for this one, we are looking for all 6 trigonometric values for 30 degrees. So I know that 30 degrees is in quadrant 1. So here's my reference triangle here in quadrant 1. This is my reference angle of 30 degrees, which makes this angle here 60 degrees. So I can see that I'm forming this special right triangle. Now for 30, 60, 90 triangles, we had a generalized case. If this were 30 and 60. This would be x, x root 3, and then 2x. I think we had it tipped on the notes, but same idea. And then 45, 45, 90. So those are my 45 degree sides. Both these would be x, and then this would be x root 2. So those are my special cases. Now in a unit circle, my hypotenuse is always 1. So I'm really looking for my x value, which is my cosine of 30, and I'm looking for my y value, which is my sine of 30. Okay. Knowing that this is my 30, 60, 90 triangle, I can kind of look at it through my special case. My 30 degree angle, across from my 30 degree angle, is going to produce half of my hypotenuse. So that's kind of one of our I'll write it this way. My short leg is half of my hypotenuse, or 2 times my short leg equals my hypotenuse, and then my longer leg is my short leg times √3. So those are kind of 2 relationships. Or you can remember the special case. Either way, it doesn't really matter. What you'll end up getting, though, is that my sine, I'll write it over here, my sine of 30 degrees, this angle right here, is going to be half of my hypotenuse. So half of my hypotenuse is my hypotenuse, which is 1 over 2. Which means that my cosecant of 30 is going to be 1 over 1/2, or flip that around, 2 over 1. For my cosine of 30, now I'm looking, I'll write this out. This is 1, this is 1/2, so this is going to be 1/2 times my √3, or √3 times my x value, which is going to be √3 over 2. And this should ring some bells when you probably did this in Algebra 2, how you came up with these ratios. Now it doesn't matter, again, like whether this is 5 or 1 or 10, when I do the ratios of it, it should reduce down to the same ratio, the same value. That's what we saw in the notes in the special right triangles, that it didn't matter if we started out with a triangle that was 10 and 10, and then 10 √2, like it should end up being the ratio of √2 somewhere in there. So if I flip that around, my secant of 30 is going to be 2 over √3, and then I rationalize, which is 2 √3 over 3. So then we're coming up with our tangent and our cotangent. What I like to do for my tangent is look at my ratio of sine and cosine, because I know that, again, like my tangent is that quotient identity of sine of 30 over cosine of 30. And I know my sine is 1/2, and my cosine is √3 over 2. So then I can come up with that ratio. We've seen this before, how our hypotenuses cancel out, but you could also just multiply by the reciprocal. But what will happen is that those will go away, and you'll have 1 over √3, and then we rationalize, and we get that our tangent of 30 is √3 over 3. And then our cotangent is the reciprocal of that, so you could flip that one and then re-rationalize, or since I already had that rationalization step kind of done over there, I'll be √3 over 1. These numbers, 1/2, √3 over 2, √3 over 3, √3, 2 √3 over 3, and 2 come up in every single 30, 60, 90 triangle that you draw on your unit circle. What changes is the sign that you're looking at, so like whether this is positive or negative, and it also changes because we have that cofunction identity depending on our reference angle. If this were 60 degrees, then all these things would flip. So instead, my cosine would then be 1/2, so these would change direction, and that would make my secant 2, and then my sine would be the √3 over 2, and my secant would be my cosecant would be the 2 √3 over 3, and then my tangent values would flip. And that's because of my cofunction identities, that the sine of 30 degrees is the same thing as my cosine of 60. So that would flip all of my ratios here. So we're going to do the same thing, but we're going to do it for 45 degrees, which makes our life a little bit easier. So here's my unit circle, or sorry, my reference triangle. Here's my reference angle, 45, 45. This value here is going to be 1, because that's my hypotenuse. And I know that my special case hypotenuse is x √2, or my short leg, my leg times √2 is my long leg. So if I was going to solve for that, working backwards, this is my x value, this is my y value, which are the same. This is cosine of 45, and this is the sine of 45. I know that 1 times, I'll write it this way, my hypotenuse equals my leg times √2, and I know my hypotenuse is 1. My leg is either x or y, doesn't matter. And so to solve for x, I'm going to divide both sides by √2. Those will go away. I'll be left with x, and then I'll rationalize. So I'll get √2 over 2. And that should, again, like ring a bell. That's also equal to y, because in a 45, 45, 90, x is equal to y. So that should ring a bell as far as our trig functions are concerned. Cosecant of 45, secant of 45, and cotangent of 45. So my sine of 45 is root 2 over 2. My cosine of 45 is also root 2 over 2. My tangent of 45 is root 2 over 2 over root 2 over 2, or we already did this like last chapter. The tangent of these two things, the ratio of y over x, is, since y and x are the same, would be equal to 1, which makes my cotangent also the reciprocal of that, which is still just 1. My cosecant and my secant, I'm actually going to look, like you could flip this and then re-rationalize, but we already rationalized over here, so if I flip that instead, I get root 2 over 1, which is just root 2, and then the same thing for secant. So again, these ratios will also appear in every 45, 45, 90 triangle that you draw in your unit circle. What changes then is the sign, whether these are positive or negative. And last one, might be already there, that's fine. This is my 60-degree reference angle in quadrant 1, 30 degree. My hypotenuse here still is 1. I know that my angle across, or my side length across to my 30-degree angle is going to be half of my hypotenuse, so that's going to be 1/2. And then my side length across to my 60-degree angle is going to be 1/2 times root 3, which is going to be root 3 over 2. And I did that a little bit faster. It's the same steps as above. The same ratios will appear, where this is going to be 1/2 and then root 3 over 2. But from here, since I know that this is sine and this is cosine, I can come up with all of my 6 trig values. And that's, I'll start with sine. That's the goal, is to get to this place and be able to do this really fast, rather than having to think about the special right triangles in that same way. Just know that across from the 30 degree and a unit circle is going to be 1/2, and across from the 60 degree is going to be root 3 over 2. And it comes from that idea of the special right triangle. So sine is my y value, which is root 3 over 2. Cosine is 1/2. And tangent of 60 is going to be my sine of 60 over my cosine of 60, which equals root 3 over 2 over 1/2, which my hypotenuses will cancel out, and I'll be left with root 3 over 1, which is just root 3. My cosecant is 2 over root 3, the reciprocal, and then I rationalize, and I'll get 2 root 3 over 3, which again, we already done. We did it up here. So 2 root 3 over 3. My secant, reciprocal of 1/2, is 2 over 1, or 2. And then my cotangent of 60, reciprocal of this is root 3 over 1, so 1 over root 3. And then I rationalize, and I get root 3 over 3. So again, although we're doing like kind of disjointed pieces, they all kind of relate to each other. Like this is all to do with more of that special right triangle stuff, but specifically we're looking only at quadrant 1 in this case, and we're noticing that again, since these are co-function identities, like example 8 and example 10, that my sine values, which was 1/2 in example 8, sine of 30, which is the same thing then as cosine of 60. So these will just end up switching places as I go through my unit circle and I'm looking at those different reference angles, which is kind of why that cofunction identity is important. And then for like these 3 different values that I'm coming up with, root 3 over 2 and 2 root 3 over 3, 1/2 and 2, root 3 and root 3 over 3, all appear in all of my 30, 60, 90 triangles. It just kind of depends on our reference angle that are located. And likewise for example 10, like root 2 over 2 and root 2 and 1 also all appear on my 45, 45, 90 triangles. It just depends on where we're located.